Hello SL2. This unit is on applications of derivatives. Our first day of notes is on curve properties, and our essential question for today is how can we use our knowledge of derivatives to understand curve properties. Okay, first I'm going to start off with some definitions, and then we're also going to take a look at a diagram of a function. So the first thing I want to talk about is this vocabulary word, monotonic function. A monotonic function is a function that either never decreases or never increases. So if I had an example of a function that never decreases, that means it would always increase. So that would be one example of a monotonic function. Another example of one that never increases would be one function that always decreased. Okay. This one is always increasing. And our function here is always decreasing. And that word monotonic should be familiar to you with monotone if you've heard of that. So think of monotone, only one sound as your voice. So a monotonic function would be one that never decreased or never increased. So it's always doing one thing. Okay. Bringing back the vocabulary word of increasing and decreasing is also important. Remember back from Algebra 2 when we started talking about increasing intervals and decreasing intervals, we're examining our graph always from the left to right, and we're looking at the increasing intervals with the comparing the y values, what's happening, and then writing down the x values. So a lot of times in Algebra 2 we talk about putting either a roller coaster or a little person on our left side of our graph, because we always analyze our graph from left to right, and then we talk about what's this person doing right here in this section. So this person, if you're looking at that graph and you're comparing the y's, they would always be decreasing. Our slope would always be decreasing here. So this section here would be a decreasing interval, and then at this point that little person would then start walking up our graph, our function here. So that would be a increasing interval. So remember, for increasing and decreasing, we analyze from left to right. And we write our intervals in the x values. So again, going back to this graph, this section right here would always be decreasing. Our slope here is always going down. If we think about our derivative and what our derivative is, it would always be a negative here. So that would be our decreasing interval. And remember from Algebra 2, we would write that in the x values. So our little person here is actually starting way out here on our graph. Our x values would be at negative infinity. And then this person, or roller coaster, depending on how your teacher taught it, would stop right about here. On my graph, I would have to estimate since it's not falling right on a unit. So I'm going to estimate that. It's definitely somewhere between 1 and 1.5, and I'm going to say 1.2. So that would be our decreasing interval. Remember, for decreasing and increase, you always put parentheses. You don't have to worry about the brackets. So at that same point, at 1.2 would start our increasing. Our graph would then start our increasing slope here. And it would continue all the way up to positive infinity, because our graph, this arrow means it is going slowly to the right forever. So our x value on the right end of our graph would be positive infinity. Okay, so a few more vocabulary words. The first one is this change in direction. This little point here, we will call that a turning point, a change in direction at that point. Right there. Okay. And before we talk about some more vocabulary, I want to just show you a section of this video in the Geometer Sketchpad that just shows you a nice visual of our slope of our tangent from one point to the other. So right now, our slope of our tangent is positive, as you can see. As it continues to go up in the increasing interval here, it will stay positive. And then remember, at this point right here, our slope of our tangent, our first derivative would be 0. And then, as you'll see, as it goes down here, it'll become a negative. Our decreasing intervals, our first derivative, which again, another word for that is our slope of our tangent, would be negative. And then at this point, again, we would have what would be our slope of our tangent? That's right. It would be 0 again. And then here at this point where the graph becomes increasing again would also be a positive slope. So you can see already how we're going to apply our knowledge of derivatives to our functions. This, just if you haven't seen this before, our little point is going to go along the graph, and this black line is demonstrating our tangent. Here you'll see the numbers change as it goes from one section to the other. So right now we're starting at -2, and I'm just going to have it go through and go all the way to 4.5 so that you can see what happens. Okay. So now our graph, our point will start to move, and you can watch how the slope is positive here, and at this point it will be 0 of our slope of our tangent, our first derivative, and then you'll see the slope of the tangent be negative, and then again at 0, and then increase again to a positive slope of the tangent. Okay, one more time, and we'll go backwards, just so you can see that one more time. Okay, so hopefully that was a good visual to have you see how our first derivative is going to apply here. Some more vocabulary. As we're talking about different words, you'll be needing to understand what a global maximum and a global minimum is. And they are maximum, or a global maximum is a maximum value of y that occurs at the endpoint of a domain. So see how we have an endpoint here and an endpoint there. This point right here would be a global maximum, and this would be a global minimum. Okay, and this one would be the global minimum. And again, the definition is that minimum value of y occurs at the endpoint. So see how there's an endpoint. Of the endpoint of the domain. And you can write the same thing for the global maximum. That's going to be a maximum value of y that occurs at the endpoint of the domain. Okay, so this word looks a little off there. Let me fix that. That's an occurs there. Okay, so a few more vocabulary words. We have a relative local maximum. Both of these words you'll see interchangeable, so sometimes you'll see it say relative maximum, sometimes you'll see local maximum. And again, relative maximum, relative minimum, or local minimum. And the other ones you'll see are absolute maximum and absolute minimum. And our last one that you'll see are point of inflection, and not a change in direction. So let's just create a new graph here to talk about the rest of these. Okay. So we have a function that both of our ends, if you remember end behavior, both of our endpoints are going, our ends of our graph are going to, if you think of where our end are, they're both going to negative infinity. So on our left side of our graph here, as our x approaches negative infinity, the function is going down, it's going to negative infinity. And here, as our function is going to positive infinity, or our end of our graph is also going to negative infinity. So here you can see how some of these words are going to play out. Our relative and local maximum are just that. They are maximum points or minimum points that are at our absolute here. In this case, within our domain here, we do not have an absolute minimum because both of our ends are going down to negative infinity. So in this graph, there will not be an absolute minimum. So an absolute maximum we actually do have on this graph, right? If you think about what a maximum is and the word absolute, our highest y value would be at this point here. So this point right here would be an absolute maximum. Okay, and I'm going to stop this first video here and pick up on the next video. So please click on to the next video after you stop.